Okay, so in the previous part, so we have talked about the two cross-validation approaches. The first one is the validation set approach, which is computational simple. Um, so you divide the data into two parts, training one part as the training data and the other part as the testing data. However, this approach will suffer from the high bias because every time you only use half of the information from the data, and potentially you may overestimate the test error. So secondly, so if you repeat the procedure many times, the result will be very unstable. So that's because so every time the randomly split will give you very different result, and because you only use half information from the data. So if you repeat the procedure many times, the result is highly variable. And the second approach is leave out cross-validation, the so-called LOOCV, which is computational intensive. So that is actually every time you treat each observation as the testing and the remaining n-1 observation as the training. And based on the training, you train a model, and then you get your estimated value or the fitted value for the observations for each observation. And you can calculate the mean square error for that observation. And you repeat the procedure n different times because every time you just treat one observation as the testing data. And therefore, you need to fit the model n different times. So this approach will be highly computational intensive. So we need to develop approach which can be the approach taking the advantages of both the validation set approach and the leave one out cross validation. So therefore, we introduce the k-fault cross validation here. Okay, so with the k-fault cross validation, we divide the data into k part. So for example, k can be selected as 5 or 10, and by the row sum, so because 5 or 10 always can give us a very nice result in terms of the sample performance, and we divide the data into C1 up to Ck. Well, Ck will denote the indices of the observations in part K. So there are nk observations in part K, and we have n1 plus n2, etc., plus n capital K equals to n, which is the total number of the observations. Now we can calculate the cross-validation error for the k-fault cross-validation. Okay, so the mean square error here, that means this is part we treat the case part as the testing data, and then we can calculate the mean square error. And then we need to pull over all across all the different parts because we divide the data into capital K different parts. And then we need to multiply by the number of observations from the case part, and then divide by the total number of observations, and then we need to sum over all the possible K classes. And if, for example, for the 5-fold cross validation, roughly speaking, so nk divided by n will be approximately equal to 20%, 1 over 5. Then the cross validation for the 5-fold will be so k sum over k from 1 up to capital K of the MSEs, and then you divide by 5. So this will give you the overall cross validation for the 5-fold cross validation. Sorry, this will give you the error for the 5-fold cross validation. Okay, and in terms of the MSEK, okay, so that is actually for each observations belong to the case class. Okay, so yi is the true value for the response. So yi hat is the fitted value for the observation I from the case part. Okay, so how to obtain the fitted value? So this yk hat, this is a typo. We should use the yi hat here. So yi hat is the fitted value for observation I, which can be obtained with the data. So you with the case part removed, because you treat the case part as the testing data and the remaining part to be the training data. And then you fit your model based on the training data, and based on the fitted model, you can get your predicted value for the ice observation from the case part. Okay, so this will give you y hat. Okay, so let me give you an illustrative example to illustrate the whole procedure. Suppose that we consider 5-fold cross validation. That is, we randomly divide the data into 5 different folds. The first fold here, so the orange color part will be 5 different folds. Okay, So in terms of the first fault, we treat the 11th observation, 76th observation, and 5th observation. And roughly speaking, this accounts for around 20% of the data set to be as the training testing data set, and the remaining as the training data set. And for example, for the 11th observation, Y11, so this is the true value from if we treat the 11th observation, this part as the testing data, and the Y11 hat is the fitted value for the 11th observation. Well, the fitted value can be obtained by the model trained on this part of tester of the training observations. Okay, and then based on the formula in the previous slide, we can calculate the MSE1. Okay, by using this formula. So now we can calculate the MSE1, and similarly, for the second part, we treat the second part as the testing data, and the remaining as the training data, and we can calculate the MSE2, so etc. We repeat a procedure 5 different times, but every time we just treat each orange part as the testing data, while the remaining as the training data. Then we can obtain MSE1 up to MSE5. So finally, we need to sum over all the MSEs and then divide by 5. So this will give you the cross-validation, so the error for the 5-fold cross-validation. So that's the illustrative example about the 5-fold cross-validation. Okay, so mathematically speaking, it's the same as you find, for each observation, you find a kappa function such that each observation can be projected into the part or the fold it belongs to. So capital K here is the number of folds. Okay, so go back to the next example. For example, for the first observation, it can only belong to one of the 5 different orange folds. For example, if one belong to the second fold, or 2 maybe belonging to the belong to the third fold. Okay, so for each observation, it may belong to the corresponding fold. Okay, so we denote the f hat minus k to be the fitted function computed with the kth part of the data removed. Remember, for each observation, it will belong to the corresponding part, and it can be so the fitted value can be obtained by using the corresponding. So for example, for the one's observation belong to the second fold. Okay, and the fitted value for the first observation can be obtained by training on the remaining data set. Okay. Okay, so now we have we can calculate the cross-validation error for the k-fold cross-validation. So that is actually for each observation, you calculate the loss function between the true value for the ith observation and the fitted value. Okay, the fitted value is obtained, as I mentioned, by first of all choose which part of the data is treated as the testing, and then the fitted data, the fitted value will be obtained by the remaining part of the data as the training data. Okay, and then you can calculate the true value of y and the fitted value of y. And for each observation, you can calculate the loss function and then take the average across all the observations. So in terms of the loss function, okay, so we for the L2 loss function, this part will represent the mean square error, and for the L1 loss function, so correspond to the mean absolute error. So such L1 type of loss function can characterize the robustness of the data, as I mentioned in the first lecture. And in terms of the classification problem, we will use the 0 and 1 loss function, and this result will characterize the misclassification error rate. Okay. Okay, so let's consider the difference between the 3 cross-validation type approach on the particular data set we want to illustrate. So go back to the auto data set. First of all, let's compare the ROCV and the k-fold cross-validation. The first remark is the ROCV is a special case of the k-fold cross-validation. Okay, for the k-fold cross-validation, we randomly split the data into k different parts. If we randomly split the data into n different parts, then every time you treat just one observation as the testing and the remaining as remaining n minus one observations as the sorry, as the training. Okay, so if capital N equals if capital K equals to N, then the LOCV will just be the n-fold cross-validation. So the LOCV is a special case of a k-fold cross-validation where K equals to N. Okay, and in general, K will be much smaller than N. Okay, so for example, N may be 100. K, as I mentioned in the rule of thumb selection of K might be only 5 or 10. Okay, so the k-fold cross-validation will be computationally less intensive than the leave-one-out cross-validation. Okay, so leave-one-out cross-validation is very stable, as I mentioned, because you randomly split the data into n different parts. Okay, if you repeat the procedure many, many times, every time you still get this n random allocation about the data. Okay, so exactly if you repeat the procedure n different times, many, many times, you get exactly the same result. Okay, so now if we apply the polynomial regression and we plot the mean square error for the testing data as a function of the degree of the polynomial terms. Okay, so we will get this kind of curve. Okay, so first of all, the mean square error will have a sharp decrease and then only have a very slight decrease. So as I mentioned in the previous slide, so in this scenario, we will not tend to select the minimum point of this curve, but we want to choose the point which may correspond to the relatively lower degree of polynomial, but the mean square error is relatively higher. Okay, so that is, we will allow the mean square error to be relatively higher, but it might have a sharp decrease in terms of the model complexity compared with the optimum point, which can give you the the lowest mean square error. Okay, so in this particular example, we may tend to choose 2 as the optimal degree of polynomial. Okay, so if you just repeat the procedure for the tenfold cross-validation many, many times, and different color will correspond to the corresponding mean square error for the testing data. So you can see that the curves are highly similar. And so this is a very nice signal because we do not want the curves to be very different across a different repetition. So unlike the validation set approach. Okay, so let's look at the result for the validation set approach. So on the left, this is the result for the validation set approach. You can see that so different color correspond to the different repetition. And every time you randomly split the data into 2 parts, so the number of observations you treat in the training data set is only half of the information from the data set. That actually will create very high bias and high randomness. So therefore, every time if you estimate mean square error curve for the testing data as a function of the degree of the polynomial, the curves are highly different. So this is not a good result, although it is computational very efficient. Okay, so if you are using the tenfold cross-validation, so we want the result to be highly stable, meaning that for different colors of repetition, you want the mean square error curve as a function of degree polynomial to be very similar. And in terms of the pattern, similar. In terms of the magnitude, is also similar. You can see that the tenfold cross-validation can achieve this target. And but that's computational. This is more computational efficient than the LOCV. Now, because you need to only feed the model 10 different times. For the LOCV, you need to feed the model n different times. If n is 100, that means you need to feed the model 100 different times. Okay. Okay, so let me give you another simulation scenario to compare the result for the test MSE, the true test MSE, and the estimated test MSE obtained by either the leave-out cross-validation or the tenfold cross-validation. And remember, this is the simulation data set. So we know how the data are generated, okay? And because the reason why we are using the LLCV or the tenfold cross validation, such cross validation type approach is we want to use this cross validation type approach to estimate the test error. And for the to estimate the test error, you need to know what is the true test error. Then you can make a simulated comparison. So we need to know how the data generated. Suppose we know how the data are generated, then we can generate the observations of the training data set and the testing data set. Okay, and for the testing data set, we can calculate the mean square error. So this will be the true test mean square error. Okay, so this is the training data set. And we have the test data set. If we know the data generating mechanism, we can generate a test data set, and we calculate the test MSE, which can be viewed as the true test MSE. Now we can apply Liouville cross validation or the tenfold cross validation without knowing that we have the testing data set, but we only perform such cross validation procedures on the training data set. Okay, and then we compare the performance. So you can see that we still plot the function. So this is a 3 simulated examples as we discussed in the previous slides in lecture 1. And you can see that we need to plot the mean square error for the testing data as a function of the degree of the flexibility. Okay, so the flexibility moving from left to the right, we increase the model flexibility level from small to larger. Okay, and you can see that the blue solid line is the true mean square error. So it has a U shape, and the minimum point is around here, about 6. But if you are using the Liouville cross validation or the tenfold cross validation, so we use this approach to approximate the true mean square error. If you have this plot, you can see that both of the approach will give you very similar result, meaning that the LLCV and the tenfold cross validation will give very similar performance in terms of mean square error. Not only the shape, but also the minimum point. You can see that the minimum point by the either the LLCV or the tenfold cross validation, they are very close. And they are not very far away from the minimum point by the true test MSE. So here, these values are around 9 here and the 6. So 6 is not very far from 9, but it is slightly different. Okay, so that's the first simulation example. And in the second simulation example, we have a similar result in terms of the true test MSE and so it's a black solid curve. It's also U-shaped. And in terms of the LLCV and tenfold cross validation, it has a very nice U shape, but the minimum point is still slightly higher than the minimum point by the test MSE. Okay, so although the boundary part is quite different, but this part is not something we are very interested in because we are interested in find the minimum point of the cross-validation curve. Okay, so later I'm going to talk about why we have very bad result as the flexibility increase, because now you fit a polynomial regression, and if the polynomial order, higher degree of the polynomial order is included in your model fitting procedure, so you will produce a very uncertain estimate. Okay, and in terms of the last simulation example, we have a very nice result. You can see in terms of the shape, it's quite similar between the true test MSE and the estimated test MSE, either by LLCV or the tenfold cross validation. And in terms of the minimum point, it's still very close. So it's only it's all around 10. So that means, in general speaking, LLCV and the tenfold cross validation, both of them can produce somehow relatively accurate estimate for the true test MSE. Okay. Okay, so next we are going to discuss one of the most important issue in the K-fold cross-validation, which is the variance and bias trade-off. Remember, in the first lecture, we talked about the variance and bias trade-off, and this is one of the key concept in the machine learning. And because for each machine learning method, we need to find the one which correspond to the minimum point on the error for the testing data. Okay, and so each approach may have the variance and bias, and compare the performance of different approaches. You may need to do some basic variance and bias trade-off analysis for each approach. And in terms of the cross-validation procedures, we have already talked about. So let me consider some variance and bias analysis. Okay, so which one is better, ROCV or K-fold cross-validation? Of course, in terms of the computational efficiency, K-fold cross-validation is better. Okay, in the previous simulated example, we found that the K-fold cross-validation and ROCV, they have very similar sample performance. Okay, and computationally speaking, ROCV is more challenging. So so this will say that maybe we can use the K-fold cross-validation. So how about the variance and bias trade-off analysis between the two cross-validation procedures? Okay. And in terms of the N-fold, K-fold, ROCV, so every time we treat one observation as testing and the remaining N-1 observation as testing. Okay. So this will actually not have a relatively high bias issue, because we almost use almost all the information from the data as the training data set. However, if you consider the K-fold cross-validation, you only use a K-1 divided by K as big as the original of the training data set. So for example, if K is 5, then you only use 4 over 5, which is 80% of the data as the training observation. Okay, so actually that will make the prediction error to be biased upwarded, because you do not use the all the information from the data, compared with the ROCV that you almost use all the information from the data. So how about the variance? Okay, in terms of the bias, so ROCV and K-fold cross-validation. So K-fold cross-validation will have a relatively larger bias. And what about the variance? So we will expect that ROCV will have a relatively higher variance than the K-fold cross-validation. Okay, so why is that? Okay, so let's consider the definition about the K-fold cross-validation. That is actually 1 over K, okay, sum over I from 1 up to capital K, and MSEI here. Okay, so you divide the data into K different parts. Okay, you estimate you MSEI and you repeat the procedure K different times and then calculate the sample average. Okay, so now if you calculate the variance of it, so that actually will be, okay, so 1 over K here will be a constant. If you calculate this variance, that will be 1 over K squared. And then you need to consider the summation of I and the summation of I prime, okay? And the covariance between, so MSEI and MSEI prime, okay? So roughly speaking, for different MSEs, we treat them as a random variable. If they are independent, their correlation will be 0. So we do not need to consider the covariance term. But here, we need to consider not only the variance term, which is the case that I equals to I prime, but also for I not equal to I prime, we need to consider their covariance. Okay, so now suppose that we assume that the variance of MSEIs are constant. So we treat it as a sigma square. And the correlation between MSEI and the MSEI prime equals to rho here, okay? Meaning that for I prime, so for different MSEs, they will have a constant correlation. And then this part will just become 1 divided by K squared times I now equal to I prime times the covariance will be rho times the variance of each term. And then take the square of it. So that will actually become rho times sigma square. And then you plus 1 over k square and the sum over all the observation. Now you consider variance term. So the variance term will just be sigma square here. Okay, so now you consider the LOCV. So LOCV is the case that k will be equals to n. Okay, so remember what is LOCV? So every time, let's go to the illustration on the LOCV. So every time, so for example, for the first time, you treat the first observation as the testing and the remaining as the training. And for the second time, you treat the second observation as the testing and the remaining as the training. So you can see that compared with the number of observations in both of the two training set, so it have a very high overlapped number of observations. So you can see that from the observations, the third observation, even up to the nth observation, these are the common observations from two different training sets. Okay, and then if you calculate, so remember, so there's only one difference. Okay, sorry, there's only one different point. For the first one, only the second one is additionally included into the training set. And for the second one, only the first observation is additionally included in the training set. Okay, so this will actually make the training set to be highly similar. Okay, so if you calculate the mean square error, the mean square error will be very similar. So that will actually make the correlation between the mean square error to be very high. Okay, from that perspective, so if we consider LOCV here, this row will be quite close to 1. Okay, if this part is 1, okay, so that's consider extreme case, meaning that the correlation between MSE I and MSE I prime for I not equal to I prime, they are almost perfectly correlated. Okay, so this part will actually rho will be equal to 1. Okay, so now if you consider the variance of the mean square error for the leave one out cross validation, okay, so this part will be very large, and this part, if you combine this part, okay, so that actually will be 1 over n squared times n minus 1 times, now we treat rho as almost 1, so we treat as 1 sigma squared and plus 1 divided by n squared times n times sigma squared. Okay, so this will be the case that, okay, so both the variance and the covariance, they're almost the same. Okay, so it will be the same magnitude of sigma squared. So that actually will make the variance to be very large. Okay, but for the K-fold cross validation, we will have a relatively lower correlation between MSEIs and MSE I primes. So therefore, the underlying rho will be far away from 1. It will be much smaller than 1. Okay, because if you look at a illustrative example here, okay, if you consider the training data set between the first fold and the second fold, okay, in terms of the first fold, this part is treated as the training observations, and the second fold, so this part is the number of observations for the test for the training data, and the common number of observations, the common observations will be the circled part. Okay, so there are still big difference in terms of the training data set for different folds. Okay, so therefore the rho for the K-fold cross validation, if K is much smaller than n, will be much lower than 1. Okay, so it will be closer to 0. As n moves more and more far away from n, rho will be more and more closer to 0. So therefore, if you calculate the mean square error, if you calculate the variance of the average the mean square error for the cross validation, K-fold cross validation, that actually will make it the variance to be relatively small. Okay, to sum up, so to summarize, so the LOCV will have a relatively higher variance than the K-fold cross validation. Okay, so let's give a general conclusion. That is, to compromise, we will use the k-fold cross-validation with k equals to 5 or 10 as a rule of thumb in the practice. Okay. So it has been shown empirically that so both the 5-fold cross-validation or the 10-fold cross-validation that will suffer neither from high bias or high variance. Okay, so so computationally speaking, it's more efficient than the LOCV, and is less efficient than the validation set approach. But we know that validation set approach will suffer from high bias. And empirically speaking, LOCV and the k-fold cross-validating will have a very similar performance. But to save the computation for us, in practice, we will use the k-fold cross-validation, or more specifically, we will use the 5-fold cross-validation or the 10-fold cross-validation. Okay, so that's apply the cross-validation on the classification problem we have talked about in the second lecture. So this is still the two-class classification problem and a two-dimensional problem, including X1 and X2. And we have the orange class and the blue class. And this is a simulation data example. We know how the data are generated. So we can easily calculate the true posterior probability, and the Bayesian decision boundary is the are the points such that the posterior probability for the orange class is the same as the posterior probability for the blue class. Okay, and then we can calculate the base error rate, okay, which is the minimum error that one can have for this learning task. And this is also the unavoidable error. Okay, and there is a homework problem to help you to calculate the base error. Okay, then this is a simulation data example, and we know how the data are generated. So we want to apply the cross validation to select the optimal polynomial order that is included in the logistic regression. Remember, for the logistic regression, we can do it for the two-class classification problem, and we only can have the linear term. But in order to characterize the nonlinear pattern or the nonlinear decision boundary, we may potentially include some higher polynomial degree in the logistic regression. Okay, so and then we can apply the cross validation procedure to select the optimal degree of the polynomial. Okay, so first of all, we choose the that we only include the linear term. So you can see that by using the logistic regression, our decision boundary is linear, which is quite far away from the true decision boundary. If you are using the not only the linear term, but also the quadratic term, you have the quadratic decision boundary now is nonlinear, but still far away from the very nonlinear curved base decision boundary. Okay. So we want to increase the polynomial order. So you can see that increase from 3 or 4. Okay, so we get more nonlinear pattern. Okay, so now we need to actually choose what is the optimal polynomial order that one need to use. Okay, so so the blue solid line represents the training error. So the brown solid line corresponds to the test error. And again, we know how the data are generated. So we know what is the true test error. Okay, so we can generate the data, one as the training and the remaining as the testing. Okay, so we can easily calculate the true training error on this part and the true test error on this part. Now we can use the cross validation to estimate the test error. So we apply the cross validation procedure only on the training data set to estimate the test error. Okay, so you can see that on the left, this is the test error rate. In the classification problem, this corresponds to the misclassification error rate. Okay, and it's a function of the order of polynomial term that is used in the logistic regression. Okay, so you can see that in terms of the test error, so it is U-shaped. And if you're using the 10-fold cross-validation to approximate the true test error, it's also U-shaped. Okay, so in terms of the pattern, quite similar. In terms of what about the optimum polynomial order? So you can see that if you apply the if you consider the true test error, the minimum point correspond to the optimal polynomial order equaling 3. But if you are using the tenfold cross validation to estimate the true error, so the optimal polynomial order is around 4. Okay, 3 and 4, they are quite similar. Okay, so so although it's numerically it's slightly different. Okay, so now we have we can also calculate the training error denoted by the blue color. Okay, so you can see that ideally speaking, we will expect the training error will decrease as the order of the polynomial used increase. However, we have some pattern like the follows. So first of all, well, we have a decrease, sharp decrease, and then slight increase, and then finally have a sharp decrease. This sounds like not sensible, okay? But if you just look at the overall pattern from the low polynomial order and the high polynomial order, so overall speaking, there is still a downtrend, okay? So this is the result. Also because from the difference between the population level result, which is the true test error, and the sample test error. That is actually, if you estimate the mean square error for the training data set, if you calculate their expectation, then by some mathematics you can show that so this will decrease as the model flexibility increase. Okay. However, this is the so the training error we calculate here is the sample mean square error. Okay, but this mean square error is calculated from the data. This is not actually calculated from the expectation. Okay. Now, by having some randomness, we will have some fluctuation. Okay. So theoretically speaking, as the model become more flexible, if you calculate expected value for the mean square error for the training data set, it will actually decrease. But we need to calculate the sample version of it. So because of the randomness coming from the data, so it may have some small fluctuation. But overall speaking, it will still have the downtrend. Okay. Okay. So that's the first cross-validation approach on the logistic regression, and we can also apply the cross-validation approach on the k-nearest neighbor. Remember, the k-nearest neighbor can control the flexibility level of the model. As k equals to 1, 1 over k is 1, which is the most flexible approach. If k, for example, is 100, then 1 over k is 1%. This is the less flexible approach. Then moving from the less flexible to more flexible, okay? So that is actually move from the left to the right on x-axis. So you can calculate the error misclassification error, okay? So in terms of the true test error misclassification error is U-shaped. In terms of the estimated test misclassification error, so it's also overall speaking, it's also U-shaped. Okay, and in terms of the optimum number of neighbors, so both of them will roughly suggest 0.1, which equivalent to say that so k can be roughly speaking selected as 10 here. Okay, and in terms of the training error, we can see that as the model become more flexible, the training error will decrease. Okay. Okay, so that's all for this part.